Atmospheres of Titan. Titan, the largest satellite of Saturn, has a thick nitrogen atmosphere. At its surface, the pressure is 1.5 Earth atmospheres and the temperature is 94 Kelvin. A. What is the surface temperature in degrees Celsius? B. Calculate the surface density in Titan atmosphere in molecules per cubic meter. C. Compare the density of Titan's surface atmosphere to the density of Earth's atmosphere at 22 degrees Celsius. Which body has a denser atmosphere? Okay, so let's see what they ask us to do first. Question A, the temperature in Celsius. Okay, easy, right? Temperature in Kelvin, we just have to convert into Celsius. And this is the equation, right? Like if we know Celsius, we plus another 273, we will have Kelvin. So just the other way, if we want to find TC, we just have to move 273 Kelvin to the other side, or just got the Kelvin subtracted by this amount, then we got the degrees Celsius. So that should be 94 here, subtract by this amount, then we got it to be minus 179 degrees Celsius. Okay, oh, it's pretty cold, right? Okay. B. Calculate the surface density. Okay, surface density in molecules per cubic meter. You see that they mention some units here. In physics, it's very useful to make use of the unit because it can also help you to derive which equation you can use. So here, let's see, that should be molecule, number of molecules then, over a meter cube. So I guess in order to count the number of molecules, that should be the big N, right? And which quantity that will be measured in meter cube? That should be the volume, right? Yeah. So actually they ask us to find the density, but it's not like the usual density as mass over volume, but that should be the number of molecules over volume. Okay. So how can we do this? Think about what's given in the problem statement. The pressure is provided, the temperature is provided, pressure, temperature, and that also related to volume. Well, so I could say it could just like make me think of that equations, right? Yep, this is the equation PV equals nRT, the equation of state for the ideal gas. Okay, so then we know very well from other problems previously that N equals to the big N as the number of molecules over the Na, and Na is the what? Is the Avogadro numbers, right? Which is a huge number. 602 billion trillions of molecules in a mole, right? That's the Na. So if we just rearrange this equations a little bit, we can solve for the N, or we can just substitute this one into this equation, and what we need to find is this ratio, right, of the N over the V. So I will just keep N over V, so I need to move V to the other side by dividing it here, and then I move Na to this side, and also RT to this side. Then what I got is that the density would be what? The pressure over RT times with Na, right? Do you agree? It's just like a math arrangement here, right? And then just plug in the values. Do we know the values of the pressure? Yes, right? They provided that. And they just said it's 1/2 of the Earth atmosphere. And actually, my atmosphere is just the unit, right? The unit atmosphere itself. And we know that why do we need to convert it to Pascal? Well, because it's mentioned in meter cube, right? And we know then it should be in the SI unit. And then because Pascal is that 1 Pascal actually is 1 joule over meter cubes, right? So if we got the R values also in joule, then we can have the joule cancel out because the Pascal here means that joule over meter cube. Then we can have the meter cube left as the unit. So this is just plug in the values, and you can see that on the unit will cancel out, and what left is just the number of molecules over the meter cube. Sounds good? So then we done with question B as well, and that's pretty huge, right? Like 1.17 times 10 to the 26. That's a lot. Now they ask us to do the same for the Earth. Well, and also at another different temperature, which is like this is like very cool temperature that people will enjoy. I don't think that anyone will enjoy this temperature. We could have been dead with it at this temperature. Okay, so anyway, back to this one of the Earth. Just plug in the values, right? The same thing. And remember, you have to convert the unit, degree Celsius, back to Kelvin, right? Because these equations only work with temperatures in Kelvin. Remember that, okay? In Kelvin. And then you can find this is the number of molecules per a cubic meter for the Earth. Now they also ask us to compare it between the Titan, Earth and Titan. Which one has denser atmosphere? Which means that we need to compare the density, and obviously we can see this one like 10 to the 26, this is just like 10 to the 25. So this one should be like around 10 times 10 to the 25, right? 25th, sorry, 25th. So then that should be about 5 times, 4.7 times denser, the Titan. So then the Titan has a denser atmosphere. So, see? So I could say that what to take away from this problem is that make sure that you know what you need to find. Always ask yourself what you need to find for each problem statement, and then from there try to symbolize it, express it as a symbol in physics, and then later after that you can like think about which equation that will contain on the given data and what you need to looking for. I hope that it could be helpful. Please let me know if you have any question. Okay, thank you.